So now that we've seen what the binomial theorem is, let's take a look at some specific examples. I made the claim that we can use this to multiply out polynomials, or excuse me, multiply out binomials like a plus 2 to the fifth, the example that I've got here. And that we can use it to do this really quickly. Okay, so this first one, I really am going to use the formula itself to do this, because if you ever have some situation you want to write a computer program to do this, it's really pretty straightforward, but you need to be squared away on what the formula is saying. So let's start from here, right? For us, for my example, n is 5, and one more, n is 5, and b is 2. All right, so let me write this out a little cleaner here. K equals 0 to 5. 5 choose 0. A to the 5 minus k, b to the k. Okay, so let's write this out. Right, and the way I do this, I kind of do it in separate parts. I do the coefficients first, right? K, whoops, excuse me. Should be 5 choose k here, not 5 choose 0. So the coefficients are going to be 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and I should have started a little, as a matter of fact, I'm going to write it again. Let me start just a little, start all the way over at the edge. Right, this is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Now, what are the coefficients? Well, when k is 0, this is a to the 5 minus 0, that's a to the 5th. When k is 1, it's a to the 4th. And they just keep walking down. A cubed, a squared, a to the 1st. Finally, when k is 5, that's a to the 0, which is just 1. So there is no a on the last one. Now, what do the b's do? Well, they do the same thing in reverse. They start at b to the 0, so there's no b term here. Then it's b to the 1st, b squared, b cubed, b to the 4th, and finally b to the 5th. And we have this sum here, right? So that's saying add all of these together. Right, now I just need to turn all those combinations into numbers. But remember, we saw the rows of Pascal's triangle, really technically it's the 6th row, the one that starts with 5. Let me write it out. Pascal's triangle is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, and 1. Now, you remember back when we talked about Pascal's triangle, I made a special point of pointing out that this diagonal here is 1, 2, 3, 4, 5, and this diagonal here is also 1, 2, 3, 4, 5. Right? The reason I did that is that makes it really quick and easy way to tell which row you need. If you're doing something plus something to the 5th, you need the row that has a 5 in that second position. Right, so you're welcome to work out all of these combinations if you like. I'm just going to pull the numbers from the triangle. This is 1a to the 5th plus 5a to the 4th b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the 4th plus 1b to the 5th. And that's it. We're done. There's the expansion. Right? That's it. I'd like you to stop and think for just a second about how long it would have taken you to do that the algebra way and write out a plus 2 times a plus 2 times a plus 2 times a plus 2 times a plus 2. Multiply them all out 2 at a time. We'd have been here for, I mean, I could knock it out pretty quick, and it would still probably take me the better part of 5 minutes, right, to do that. Here, I mean, this is all there was to it. Okay, so let's look at another example. Right, this one is a little busier, right? It's not there's no number there. There's a second variable, the minus 2y, and there's a minus sign, right? If you look back at our formula, it says a plus b, not a minus b. Okay, but that's okay. Look, I want you to think of this as being just x plus minus 2y to the fourth. Okay, so where I was putting, I think it was a 2 in the last problem, right? Everywhere I had a 2 in there, I'm going to have a minus 2y. So I'm going to do this exactly the same way, right? This is, I'll do the coefficients first. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Then I'm going to do the x's. X to the fourth, x to the third, x squared, x to the first, and there's x to the 0, which of course you can write it in there if you really want to be complete, finish the pattern, but that's just going to be 1. Now I'm going to do the same thing with the minus 2y's. Minus 2y to the 0, minus 2y to the first, minus 2y squared, minus 2y cubed, minus 2y to the fourth. Add them all together. All right, now how about these coefficients? Well, again, you're welcome to work out all those combinations if you like, but Pascal's triangle is your friend here. This is 1 x to the fourth times 1 minus 2y to the 0 plus 4 x to the third negative 2y plus 6. Remember, we did this on the last slide, right? We had to get this row to go on to the fifth one, which is why I knew that was going to be a 6 there. X squared times 4y squared plus 4x negative 8y cubed. So you see, the negatives are going to come back into this. Plus, whoops, I already got the plus in there. Plus negative 2y to the fourth, which is 16y to the fourth. Now we just have a little more multiplication to do. This is x to the fourth minus 4 times negative 2 minus 8x cubed y plus 24x squared y squared minus 32 xy cubed plus 16 y to the fourth. And that's it. We're done. All right, we're done. That's all there is to it. All right, there's our expanded version of that binomial. All right, now you've got an idea of how how the binomial theorem connects to Pascal's triangle, how we can use that to write out these binomial expansions really pretty quickly. So what we're going to do in the next lecture, will be the last one in this series. We're going to look some more at combinatoric proofs that build in part on these things we've been talking about here with the binomial theorem and Pascal's triangle.